So welcome to today's lecture. Today we will be continuing our discussion on matrix concentration, and the agenda for today's lecture. Today's lecture will be relatively short because you'll get to know why. So the agenda for today's lecture is that first we will start with the transfer rule. So transfer rule, we talked about it in the proof for matrix Chernoff bounds, and actually I said that we will discuss it after we finish the proof, but I forgot to discuss that. So transfer rule basically relates the function on scalars to the semi-definite order on matrix functions. So we'll see what the transfer rule is. Then we will discuss matrix Bernstein inequalities. Okay. So we will not look at the proof for matrix Bernstein inequalities in great detail because the ideas that they have used for the proof is has a lot of similarities to the proof of the matrix Chernoff bounds, which we looked at in the last lecture. We will primarily focus on the major differences or on the main ideas that are different in this proof in the proof for matrix Bernstein inequalities compared to the proof of the other of the matrix Chernoff inequality. So these are the two agendas. This is the agenda for today. Okay, so we will start with the transfer rule. Okay, so the transfer rule says that if f and g, let f and g be real valued functions defined on an interval I of the real line, and A be a Hermitian matrix. Okay, example that A be a Hermitian matrix whose eigenvalues are contained in I. So in the same interval. So the interval I on which the functions f and g are defined, the eigenvalues of a Hermitian matrix A are also contained in that interval. Then what we have is that if f of A less than equal to g of A for all A in I, this implies that f of matrix, the Hermitian matrix A, is on the semi-definite order G of Hermitian matrix A. So if we recall, what this means is that G of A minus f of A is positive semi-definite. So this is what this order means, that G of A minus f of A is positive semi-definite. So this is one of the rules of porting a function, porting the monotonicity of functions defined on scalar to the monotonicity in the semi-definite order on the same functions defined using the matrices. Okay. So last class, we saw an application of this transfer rule without really stating what this transfer rule is. We said that in the proof for Chernoff bounds, we said that E of theta x okay, so if you recall, this was in the proof for the MGF and CGF bound. In the first part of the proof, we used the convexity property of the exponential function to derive this relation. Then we said that since this is true for all scalars x in 0 to L, then for a matrix X, is the same thing will be true, and we had that lambda min of x is greater than equal to 0 and lambda max of x is less than or equal to L. Okay, so this was an application of this transfer rule which we saw in the last class. We will be again invoking this transfer rule in the proof of matrix Bernstein inequality that we will discuss today. I'll just briefly describe the idea of the proof of this transfer rule. Okay, so the proof revolves around three ideas. The first is that if f of a is less than or equal to g of a, then if we have a diagonal matrix, then this observation is true because capital lambda is a diagonal matrix. Then we say that since A is a Hermitian matrix, it has uh, it has an eigenvalue decomposition in the following way. So we can write something like this: f of capital lambda q star is less than or equal to q g of capital lambda q star. Okay, this is also known as the conjugation rule. The monograph that we are referring to, this is called as the conjugation rule. This needs proof that if f of lambda on the semi-definite order is less than g of capital lambda, then multiplying it on both sides by unitary, I mean, or the orthogonal matrices does not change the order. Okay, that it is monotonous. So I encourage you to work on this proof. Uh, so basically, the main idea that we have to use here is that if A is, let's say, positive semi-definite, then B A B star is also positive semi-definite for any B. Okay, so you just think about why this is true. You can refer to several online resources. I think this can be easily found on Google. Why is this true? Okay. Yeah. So once this observation is established, then we get a proof of transfer rule directly by the definition of standard matrix functions. Okay, so if you recall, we said that the standard matrix functions are those which apply only to the eigenvalues of this. Okay, so when we say f of a, then we will take an eigenvalue decomposition. What we will get is q f lambda of q star, and the rest of the proof is quite simple. Okay, so this transfer rule is an important uh, side result or an important small little result that we will use in today's proof as well. Okay, so this tells us how we can port the orders or the inequalities from the scalar case to the functions of matrices. Okay, so next we will get started with the what do you say, the matrix Bernstein inequality. But before going into the matrix Bernstein inequality, I mean, right now I'll not even state that. We will just look at the proof, like what we did in the Chernoff bounds case was that we first developed bounds on the MGF and CGF, and we used those bounds to prove and we used the bounds on MGF and CGF to prove the inequality which we were interested in. We will follow the same kind of flow today as well. And in the first step, we will prove the bounds on MGF and CGF. Okay. So we start with a lemma. Okay. So what this says is that let X be a random Hermitian matrix. Okay. Then we assume that 0 theta. Okay. This is the first assumption, and then the second assumption is that the largest eigenvalue is upper bounded by L. Then for theta lying in between this interval, we have expected value of e raised to the power theta x exponential theta square by 2 1 minus theta L by 3 into expected value of x square. Okay, so this is the first. Then the second, this is the bound on MGF. Like as we did last time, if we take logarithm on both sides, then we will get the bounds on CGF. Okay, so it might give us good insights if we compare this bound with the bound that we obtained in the case of Chernoff. So we'll just write it down on the side. So for as a side discussion, in the last lecture, when we proved the MGF and CGF bound for Chernoff, we got something like this. Okay, so this is we obtained this as the MGF bound for the Chernoff. So if you look at the difference, apart from the constants, the major difference is that the Bernstein inequality uses information about we can say variance. Okay, because we will be assuming zero mean random matrices. It's so this the Bernstein bounds, it uses information about the variance as well. On the other hand, this works only with the mean. So this is there are some parallels between them, and the main effort in the proof is to somehow expose the x square term. When so we will start by taking the expectation of e raised to the power theta of x, and then our endeavor will be to expose the x square term so that we can somehow bring it into the picture. Okay, so that will be our first step. Now we will start with the proof for this case. Since we already talked that we want to expose x square, we'll start with first the matrix exponential theta x plus, I mean these are just some tricks. So we can write it like this, and then we define a function f of x Okay, where f is a function on real line. Okay, our objective is to use the transfer rule. We define f of x is e raised to the power theta x minus theta x minus 1 divided by x square for x not equal to 0, and f of 0 is theta square by 2. Okay, so this is what we have done. If you see from here to here, now we will prove monotonicity on the scalar function. Then we will use the transfer rule to port that monotonicity to the semi-definite operator as well. One can verify that f of x is an increasing function. I mean, we can just simply plot it and see, because at this point of time, we are not interested in working out unnecessary calculus. We can just plot it and see that f of x is an increasing function. Now, because it is an increasing function, we have, okay, now this is uh, the inequality. Then we have assumed that the eigenvalues of x do not exceed L. Okay, so we can apply the transfer rule. Okay. Next, what we do is that we use the, I mean, when we apply the transfer rule, that is one thing, and then in parallel we also use the conjugation rule. Conjugation rule we saw earlier that if we multiply it by q and q star, the order it does not change. Okay, so if f of lambda is less than g of lambda, then if we multiply by q and q star, then the order does not change. So in this case, what we will have is that we can write, okay, so we had x fx x, and then f of x we replaced by f of L, and that replacement does not change anything. So what we will have is I plus theta of x plus f L into x square. Okay, so this is uh, so this is what we get. Okay, so next we develop an estimate for f of L. So we have f of L is given by theta L minus theta L minus 1 divided by L square. So this can be written as 1 over L square summation q is equal to 2 to infinity theta L Q divided by Q factorial. So we have just expanded the matrix, we have just expanded the exponential function. Next, we, okay, so we can just rewrite, simplify it as Q is equal to 2 to infinity theta L Q minus 2 by Q factorial. So Q factorial we can write as, Q minus 1, 4, 3, 2, 1. Okay. So this is clearly greater than, we replace everything by 3. Alright. So what we will obtain is 3 to the power Q minus 2 into 2. So this is the inequality that we substitute here. So what we have is that f of L is now less than or equal to theta square by 2. Q is equal to 2 to infinity theta L Q minus 2 by 3 raised to the power Q minus 2. Okay, so now this just becomes an infinite sum of a geometric progression, and when we work it out, we get this sum as 1 minus theta L by 3. One consideration here that we need to have is that theta L by 3 should be less than 1 for the series to converge. Otherwise, there will not be a convergence. So theta L by 3 should be equal to, I mean, should be less than 1. So then we have an upper bound on the value of theta. Theta is less than 3 by L, and this is what we had here in the statement. So that is how this particular condition comes into picture. Now, once we have established this, then the proof is almost done. So we had this expression earlier. So we just replace f of L by what we have found now, theta square by 2 divided by 1 minus theta L by 3 into x square. Now when we take expectation, our objective was to expose x square, and we have done in that successfully. Then expected value if we take on both sides, then I, and then we assume that expected value of x is 0, which we will be using in the Chernoff, in the Bernstein inequality anyway. So we have theta L by 3 e raised to the power x square. This is less than or equal to exponential of theta square by 2 1 minus theta L by 3 into of x square. So we have used 1 plus x is less than is equal to e raised to the power x. Now the CGF bound can be obtained by taking logarithm log on both sides. Okay, so the CGF bounds can be, so we'll not discuss that in detail. All right. So now that we are done, we will next dive into the proof for the matrix Bernstein inequality. Okay, so I'll just write the statement of the matrix Bernstein. It is, I think in the first lecture we discussed the matrix Bernstein inequality and its application to the sum of to the covariance matrix. Okay, so we have already seen the matrix Bernstein inequality. We had a variance statistic and whatnot. Okay, so we have SK is a finite sequence of independent random matrices. Okay, so independent and random matrices with dimension d1 cross d2. Okay, we are not saying that they are Hermitian. Although we will, in the proof, the flow of the proof is such that we will first prove it for Hermitian matrices. Then we will use a particular method of Hermitian dilation, with which we can say that it will work for general independent matrices as well. So this is the first consideration. Then the second consideration is that they are all zero mean. So 0 will be a matrix. And we have that the largest eigenvalue, the largest singular value is bounded for all k. These are the three things. Then we introduce the sum matrix Z. This is the sum of all the matrix. Then we have, so there are a lot of things in the statement itself. Then we have a variance statistic. Okay, we have a variance statistic. So V of Z is equal to max of or okay. So this can equivalently can be written as, I mean, okay. So this is the variance statistic. Then then comes the statement of then we have that expected value of the spectral norm of Z, which is just the largest eigenvalue, is less than or equal to 2 times the variance statistic log of d1 plus d2 plus 1 by 3 L log of d1 plus d2. Okay, so this is and for all t greater than or equal to 0. Then the other bound that we have is on the probability that the spectral norm is greater than t. Okay, so we will not be proving this in an exact way. We will just discuss the flow of the proof and some important ideas that are used for proving the same. So that is how we will be doing it, because much of the proof is similar in flavor to the proof of Chernoff bounds, and it is unnecessary repetition, I mean, from my point of view. Okay, So we will do it in two steps. In this first step, so for scribing the lecture, so that the scribe, whoever is scribing this lecture, can just mention these same things. So the scribe also does not have to do the whole proof. Uh, okay. Rather, I would say that the scribe has to do the whole proof because it is sort of given in the monograph as well. It will be a good practice. It will be good practice for the scribe also. Okay. So in the first step, we will prove Bernstein for random Hermitian matrices. The random Hermitian case. Okay. So everything else is same. So we consider xk. They are independent random Hermitian matrices, and xk is 0, lambda max xk is less than or equal to L. Here, the spectral norm is the largest singular value because Z can be rectangular as well. But here, since we are considering Hermitian matrices, we can freely write it as lambda max. Then, then for proving it, as we did it in the Chernoff case, we invoke the matrix Bernstein CGF bound. Okay, and what it says, we just proved it a while ago. G of theta, expected value of xk square, where g of theta is equal to theta square by 2 divided by 1 minus theta L by 3, and we had the consideration that our theta satisfies this relation. So we just now proved this, and let y is equal to summation over all k xk. Then the proof, it sort of follows the flow of the matrix Chernoff bounds. That is why I did not want to discuss the same things again, but maybe discussing it again will help in understanding it. So expected value of lambda max. So these master bounds we proved in lecture in the second lecture of the matrix concentration inequalities, the master bounds. Uh, so this is again we have infimum theta greater than 0, 1 by theta log trace exponential sum over k log expected value exponential theta xk. All right. Then we use the second step is the same step. In conceptually, it is the same step that we did for the matrix Chernoff bound as well. We use the monotonicity of the trace exponential, and we will replace this log exponential theta xk by g theta expected value of xk square. We when we do that, we have a constraint on the theta value. Okay, we have to respect that constraint. So we will have log trace exponential g theta sum over k expected value of xk square. Okay, so this we obtained. So this step is the same as we did for the Chernoff bounds. So we can write it in a more compact manner. Infimum over again log trace exponential g theta expected value of y square. Okay, where we defined y as sum of xk's. These are independent, so when we do y square and we calculate all the multiplying terms, they cancel out and we are left with only independent and zero mean. So because of that, then we use another step which was there in Chernoff as well. We will replace the trace by d times lambda max function. Okay, so 0 theta 3 by L 1 by theta log of d times lambda max of exponential g theta expected value of y square. Okay, so this we saw in the previous proof as well. Then we will again use another step from the Chernoff bounds, and that step is that lambda max exponential we can replace exponential lambda max still have equality. So 1 by theta log d times exponential g theta lambda max of y square. Okay, then what we have is that 0 theta 3 by L 1 by theta log d times exponential. So in the Chernoff case, when we did this, we obtained mu max, if you remember. But in this case, since we started with the CGF bound and we brought in xk square, for the Hermitian case, we get the variance statistic. So this is just the differentiating term in both the proofs, and the key was actually the CGF bounds. We got different CGF bounds, so the whole flow of proof was different. Then we just break the logarithm and we will get our value 3 over L log d by theta theta by 2 1 minus theta L by 3 variance of y. Okay, so here I mean the infimum exists and the theta that minimizes this expression has also been found, but don't we will not worry about it. We will not worry about it. We'll just forget because there are no new ideas. I mean, it is just calculus. You can look at the textbook. It has okay. So maybe I'll just write it out so that you just know the monograph. It says to use mathematic or something for finding this out. So the expression is 9 log d. Okay, this is the theta that minimizes, and when yeah, so it does not really add anything to our knowledge, so we'll not be concerned about it. I will not work out the proof for the probability bound, which we had lambda max of y greater than or equal to t, because as you just saw, I mean the proofs are exactly the same of I mean the flow is exactly similar to what we had for the Chernoff bounds. The same will be true for the lambda max case as well. So we'll not discuss this in class. So, what we are interested in the last part of the last part of today's lecture, what we will be discussing is the proof for the general case. Okay, because till now we have only been talking about Hermitian matrices, Hermitian matrices. This is probably the first time that we are going into general matrix structure. So we had recall Sk independent random matrices with dimensions d1 cross d2. Okay, and they are zero mean, all those things still stand. Zero mean the largest singular value is bounded L. These two are true for all k. The main idea or the main concept, and it might be a very useful trick, is that of Hermitian dilation. Okay, so that is the main idea of how we port the result from the Hermitian case to the non-Hermitian case. We'll just briefly describe what Hermitian dilation is. Uh, the definition. So let's say we define it by H d1 cross d2, d1 plus d2. Okay, so script H is the dilation operator which takes in any matrix of d1 cross d2 dimension, and it gives us a Hermitian matrix of dimension d1 plus d2. Hermitian will be square, so of dimension d1 plus d2, and it is defined by okay. So B here is any general matrix, and the dilation of B is given by this formula. Now, a key observation about this dilation map is that when we do the square, so let us define script A as h of b. I mean, just because it will be easier to write. Then we have a square will be b b asterisk 0 0 b b b asterisk. Okay. Then if we have to find the eigenvalues for this, okay, or the eigenvalues or eigenvectors, so what we will observe is that a square of x is equal to lambda square x. Okay, where lambda is the eigenvalue of b. This is easy to verify in the sense that because if we have a vector x and if we multiply, and I mean this is the definition of eigenvalue, if we multiply, then b star x. Okay, so maybe let me just do it. So if we multiply x once, what we will obtain is, let's say, b star x1. I mean where we will obtain b star x1, where x1 is of compatible dimension. Okay, and here we will obtain b star x2. Okay, where the all the dimensions are made compatible. So b star x1 will be something. Yeah. So I mean, I think you get the idea that if lambda is the eigenvalue of b, then what will b star x1 give us? It will give us again lambda times something. B star x2 will also give us lambda times something. Then when we again multiply it by b, we will have lambda square of this. Okay. So then the main main idea is that, or the main result here is that the squared eigenvalues of the dilation H of B coincide with the squared singular values of B. Okay. So the analysis that I did earlier, multiplying it by x and seeing what we get, is not quite exactly how that should be done. So it was not technically correct. So you can just work it out yourself. I do not, yeah, because B and B star, they're not really square matrices. So yeah, so that is one thing that we have. So this is the main observation. So when we have this, then lambda max of okay. So this is the main result which we will be using. So once we have used this, everything will just fall through. So we're not really worried, and at this point we are not really worried about the proof of matrix Bernstein. We have already seen one example of how to apply matrix Bernstein for the covariance case, and we have got a general feel of how the proofs work out in this. Okay, we have to find bounds on CGF, then substitute those bounds in the master bounds, then use monotonicity of trace, and so on. Okay, so these are the main ideas, and just remember the idea that when we have to extend the bound found for Hermitian matrix to general matrices, we will use the concept of Hermitian dilation, and I mean it will work out. So we are not really concerned about a lot of details here. So yeah, so that will be all for today.